Hello guys, welcome back to Chemistry Exams Prep. This is Dr. Kulbhushan. This question was asked in MCAT exam of 2019. In this question, we need to figure out the order of dehydration reactivity of the following 4 alcohols under acidic conditions. So dehydration of alcohols is one of their most important reactions along with the oxidation and nucleophilic substitution of alcohols. Dehydration of alcohols under acidic conditions goes through the E1 mechanism, that is elimination first order. So just like the SN1 mechanism, the E1 mechanism also go through a carbocation reactive intermediate. So the question effectively becomes a question of figuring out the stabilities of the 4 carbocations that are generated by these alcohols once the OH group turns into a good leaving group H2O by acid-base reaction. So the acids used in the dehydration is generally sulfuric acid and phosphoric acids mixture. The reason for using this mixture is that if you use only phosphoric acid, then it's not a very effective catalyst, and if you use only H2SO4, it would char the starting compounds. Therefore, mainly the mixture is phosphoric acid, but a little bit of sulfuric acid is mixed to get the best results in laboratory. Because the H2SO4 and H3PO4 solution is in water, so you can show an acid-base reaction where water is the base. It takes a proton from H2SO4 and converts to a hydronium ion. HSO4 minus is the conjugate base here. So in mechanism, if you need to take a proton, you can show by using H2O as a base. If you need to give a proton, you can show that the proton is given by hydronium ion. There may be other bases present here in the reaction mixture, but for the sake of convenience and for the sake of simplicity, you can use hydronium ion as a acid which gives the proton. So we know that for dehydration of alcohols, we need to remove water from the alcohol. Removal of water is called the dehydration, and it forms an alkene. But the OH group, as it is on the alcohol, is not a good leaving group. It's in fact a poor leaving group. However, if the OH takes a proton, then it converts to H2O, which is a far superior leaving group. So alcohols are basic because the oxygen has lone pairs of electrons. You can show this OH getting a proton from the hydronium ion. So the lone pair of electrons would approach the proton and the bond between oxygen and hydrogen breaks. This gives the formation of protonated alcohol, which is having now a OH to a good leaving group. So this acid-base reaction is very fast That's the reason that this first step is not the rate determining step. The second step, where the leaving group leaves on its own, is the rate determining step. So this step is a slow step, and therefore this determines the rate of this reaction. And since in slow rate determining step only one species is undergoing the change, therefore this is called a first order reaction. So the carbocation that is generated after this leaving group leaves part is a primary carbocation. So we know that if there is a possibility, primary carbocations would transform into a secondary carbocation. And here that is possible because there are two hydrogens there. So the next step would be a hydride shift. So basically the proton along with its bond pair of electrons would move to the carbon that has a positive charge. This is called the hydride shift. So this generates a secondary carbocation which is a lot more stable than the primary carbocation. So now the next step is removal of a proton to give an alkene. So we can show how the base water would take a proton, but here we have more than one possibility. So there is a proton here and there are three protons there too. So now the question is, which proton is taken? So if we take this proton here, then the alkene would be a less substituted alkene. If we take the proton from the carbon that is a tertiary carbon, then the alkene would be more substituted. This is a tri-substituted alkene, and therefore this is thermodynamically more stable than the alkene if you take the proton off of the CH3 carbon. So now same way we can draw the mechanism in case of alcohol B as well. But we won't draw the complete mechanism. We will just see what carbocations are formed, and is there a possibility of rearrangement. So this is a primary carbocation, and there is a possibility of forming a more stable tertiary carbocation by methyl shift this time. So once the methyl shift occurs, the carbocation becomes a tertiary carbocation, and once the proton is removed, then the product would be same as in case of alcohol A. So it is interesting to see that you can take different substrates, different starting alcohols, and still get to the same product. So now the question is, which alcohol would react the fastest in these two? So the tertiary carbocation generation from a primary carbocation is thermodynamically more favored. So that's the reason that B is more reactive than alcohol A. So we can remove some choices where if there is in any choice A is shown to be more reactive than B, and which would be the choice A. So choice A cannot be correct. Now A is also more reactive in option C, which is now also a poor choice. You can eliminate choice A and C. You don't have to eliminate them at this point. You can keep going and draw the carbocations of all alcohols, and then you can come back. But if there is less time, it's important to get to the answer quickly. So let's now draw the carbocation in case of C. So in case of C, the carbocation would be a primary carbocation, which again by hydride shift turns into a benzylic carbocation. And because this is next to the phenyl ring, so there is a possibility of resonance delocalization, and that stabilizes this carbocation. Now in case of D, you can draw the carbocation. It's already got an alkene functional group there. So this is the carbocation, and once you take the proton off of the H, that is a primary carbon, then you form the product. So now notice that in this product there are two alkenes that are conjugated. Excuse me, we missed one carbon there. So this would be the accurate structure of the product alkene that forms. Now the question is, in these two, C and D, which one would be faster reaction? Means in which case the carbocation is more stable. So in case of D, the carbocation is more stable, therefore D is more reactive than C for the dehydration reactions. So D is more reactive than C. So if we look at the options, option B seems to be the most accurate option here. If we have a look on D here, it shows C is more reactive than D, which is incorrect. So now we have figured out the correct order of dehydration reactivity of these four alcohols under acidic conditions. Okay, now so let's recap the important points here. The first point is that alcohol dehydration under acidic conditions go through even mechanism, elimination first order mechanism, which goes through the carbocation reactive intermediate generation, and the carbocations can rearrange primary carbocation can rearrange to a secondary, and secondary carbocation can rearrange to a tertiary carbocation by hydride or alkyl shifts. The alkene that forms is thermodynamically more stable if it is higher substituted. Means the alkene that is tetra substituted will be the most stable alkene than the tri substituted, and tri substituted is better than the di and mono substituted, and even mono substituted is better than having just ethylene. So the carbocations that are generated in these reactions can be stabilized by resonance, inductive effect, and hyperconjugation. So I think these were the most important points. Thanks for watching. If you have any questions, please let me know.